Welcome to Train Signal. You're watching a video about TCP/IP. Now in this video, we have a lot to go over. And the reason why is, well, this thing called TCP/IP, it has just a little bit to do with computer networking. Now if you couldn't tell the sarcasm there, I'll tell you what, in today's networks, TCP/IP is, well, it's pretty much everything. So anyway, what are we going to talk about in this video? Well, first of all, we're going to start off with the TCP/IP protocol suite. So we're going to get right in and look at the architecture of the TCP/IP protocol. Then, after we get into the architecture of the protocol, well, we're going to get into the architecture of these things called IP addresses. Now, I'm sure you've heard of an IP address before, but we're going to get right in there and see exactly how it's made up and how it works. After that, we'll go in and take a look at how to plan for an appropriate IP addressing scheme for different networks that are out there. And after that, we're going to get into what's everybody's favorite part, working with binary numbers. Yes, that's right. Time for a math lesson. Now, if math intimidates you, don't worry, because I'm going to show you how to do this in a very simple way. Now, after we're done with that fun math lesson, we're going to get into something called internetworking. Inter, of course, meaning between, so between networks or working with multiple networks. And then from there, we're going to get into something called class-full versus classless interdomain routing, or as you can see here is notated with CIDR. And depending on who you ask, that acronym is referred to as CIDR, or sometimes CIDR, or possibly even CEDAR. I've seen and heard it pronounced all three ways, and, well, I don't care how you pronounce it, we're going to talk about what it is. After we're all done with that, we will wrap up this video by going over the fundamentals of a new version of IP called IP version 6. Alright, well, is that enough for you in one video? Well, go ahead and strap your seatbelt on, because we're going to get rolling right now. So to get things started, we're going to start off with the TCP/IP protocol suite. Now the first thing I want you to know is that the letters TCP/IP stands for Transmission Control Protocol, Internet Protocol. But what I really want you to know is what TCP/IP is all about. And TCP/IP is the basic communication protocol of the Internet. Oh, so that's why TCP/IP is so important. Yeah, because without TCP/IP, guess what? We don't have, well, this little thing called the Internet. Now, even though TCP/IP was designed to be an Internet protocol, it also can, matter of fact, I shouldn't even just say can, but is being used as the primary communication protocol in most of today's private networks as well. Okay, so TCP/IP is not only required to have internet, but it's also used for most of today's private networks as well. And why is that? Well, because it makes it easier to get today's private networks out on the internet. All starts to make sense, right? Now, the TCP/IP architecture itself is based off the 4-layer DARPA model. Now, each layer of this thing called the DARPA model corresponds roughly to one or more layers of the 7-layer OSI model, which we just talked about in the last video. Now, one other thing that we learned in the last video is that when we have these different layers all working together, in this case we have the 4 layers, each of those layers will then have individual protocols which all work together to then form a protocol stack, or what is another word for suite. Okay, so just like what we saw with the OSI model, this DARPA model, or what I'm going to refer to from now on as the TCP/IP model, has a bunch of little protocols that all work together to make the TCP/IP protocol suite. Now here's what the actual TCP/IP model looks like. At the top up here we have the application layer, which may seem somewhat familiar because with the OSI model, well, we started off with the application layer there as well. But then we go down and we get to the transport layer. Again, another layer that we had with the OSI model. Then from there we go down and have the internet layer. And below that we have the network access layer. Now, how do these relate to the OSI model? Well, up here at the top we have our application layer, and it roughly relates with the top three, or we could easily say upper layers of the OSI model. And I will tell you before we go any further, there's not necessarily this literal 1-to-1, or in this case 1-to-3 layer relationship. Just like when we were learning about the OSI model, there is a lot of gray area to this. But just to keep this simple for the sake of understanding, we're going to say that the application layer of the TCP/IP model relates with the top 3 layers of the OSI model. Now, an easy one to remember is the transport layer, because it does have a 1-to-1 relationship with the transport layer of the same name, in the OSI model. Then if we move down to the internet layer, it correlates with the network layer of the OSI model. And this is something that a lot of people will get confused. And the reason why is because, well, in the TCP/IP model, we have this layer called the network access layer. Matter of fact, some people just refer to this as the network layer of the TCP/IP model. But see, it does not relate with the network layer of the OSI model. It relates with the bottom 2 layers of the OSI model. So you need to remember that it's the internet layer that correlates with the network layer of the OSI model, and the network access layer of the TCP/IP model is with the bottom 2 layers of the OSI model. All right, so that's basically how the layers correlate with the OSI model. Now, another thing that I can tell you about the TCP/IP model is that the way data is treated, the way it travels through the model, is exactly the same as how it works with the OSI model. And this picture might look a little bit familiar to you, because in the last video we saw the exact same thing with the OSI model. We have one computer, which we'll label the sending computer, which starts with raw data that it wants to send. That data is then sent down through the TCP/IP model. Right? In the last video was the OSI model, but here we're talking about the TCP/IP model. And at each layer, there is some extra information added to the data. This packet of information is then sent across the network to the receiving computer, where it then goes up through the TCP/IP model, and each layer then strips off the corresponding information that was added by the same corresponding layer, so as to giving this virtual straight across communication from the sending computer. And when we get to the actual receiving computer, we end up with the raw data that was originally sent by the sending computer. Now, if you're still a little bit fuzzy about how this whole communication works, go back and watch the OSI model again to make sure you fully understand how data moves from computer to computer. Now, the other thing that we need to take a look at is that each layer of the TCP/IP model has individual protocols. And up at the top here, we have a sampling of protocols that function at this application layer. And these protocols we're going to get into in more detail in a later video. Let me jump down here to the bottom, because down here in the bottom layer, the network access layer, you see Ethernet and Token Ring. These are a couple of low-level protocols that we talked about in a previous video. But here in the middle, for the transport layer, we have TCP and UDP, which we're going to go over in just a moment here. And then at the internet layer, we have IP, ARP, ICMP, and IGMP, which we're going to go over as well. So first, let's take a look at the transport layer protocols. We have TCP, which stands for the Transmission Control Protocol. This protocol is typically used when we have one-to-one communications, right? Direct communication from one computer to another. It's what's known as connection-oriented communication, which provides for what's known as reliable communication. Now, let's step away from this for just a moment and let's focus in on this connection-oriented communication. What does this mean? Well, this means that a connection must first be established before we start exchanging data. Now, the way we do this is through the use of something called a three-way handshake. Now, let me see if I can illustrate how this three-way handshake works. here we have two computers that need to communicate with each other. Well, if we're going to use TCP, then we need to first establish a reliable connection. And this is done through the three-way handshake, in which the first leg of this handshake is one computer saying to the other, "Hi, I'd like to talk to you. And here's the information about my abilities and the way I communicate. So here's the information you will need to have reliable communication with me." Okay, so that's the first leg of the three-way handshake. What happens in the second leg is the other computer says, "All right, thanks, I got it. I got your information. Here's information about me. So here's the information you will need to have reliable communication back with me." And then the third leg of this three-way handshake is the first computer, the originating computer, saying, "Okay, I got your information. So now that we both have each other's information, let's go ahead and begin talking, or let's begin transferring data." Okay, so that's how the three-way handshake works. One computer starts off and says, "Hi, I want to talk to you. Here's some information about me." Second computer says, "Thanks, got it. Here's information about me." And then the originating computer says, "Okay, I got your information. We're all set. Let's begin talking." Okay, so that's the three-way handshake that is used to set up the connection-oriented communication. Now, UDP, the User Datagram Protocol, is what's known as connectionless. And because it's connectionless, meaning we don't have to establish a connection first, well, the communication can be unreliable. Basically, UDP is just kind of like, I send it out there and I hope you get it. Whereas if I go back to TCP for a moment, part of what makes this so reliable is that with the connection, we are also going to have acknowledgments of receipt throughout. See, with TCP, it's kind of like sending a letter certified mail. You send it out, and then you get a receipt back that says it was delivered. Whereas UDP is like, well, just sending a letter through the regular mail. You send it and you hope it gets there. UDP is typically used with things like streaming multimedia, streaming video as a for instance. Right? If you go on to one of your favorite news websites and maybe they have a live video feed, or maybe you listen to your favorite radio station and you're listening to a live radio feed. Or maybe you're into sports and you want to listen to the ball game and you're listening again to a live feed of the broadcast. Well, do you think that it would be possible for those companies who are providing that audio and that video to be able to go ahead and send out and wait for an acknowledgement from everybody in the world who might be listening or watching to say that they got it? Well, no, that's impossible. So they just go ahead and using UDP, send it out there and hopefully you get it. And here's the thing, if you don't get it, right, if you're watching a video or you're listening to some audio and maybe one of the packets doesn't get to you, well, that's okay. You'll just miss a beat in your favorite song. You might miss a pitch in your favorite baseball game. Or when you're watching video, well, the news broadcaster, well, their voice might skip for a moment. But then you just pick back right up where you left off and continue watching or listening. And that's how UDP works. Now, let's talk about the Internet Layer protocols. And the first one we have is IP, which stands for the Internet Protocol. Now, IP probably will make the most sense and be the easiest one to understand out of the group here, because IP, well, yeah, it goes along with IP addresses, right? You've heard of IP addresses. Well, IP has to do with addressing. And along with those IP addresses, well, we use those to go ahead and route packets from one place to another. And actually, the internet layer corresponds with the network layer of the OSI model. And we learned in the last video that the network layer of the OSI model is where routing takes place. So again, it all starts to come together. It all starts to make sense. Now, ARP stands for the Address Resolution Protocol. And what ARP does is it resolves IP addresses down to the actual physical hardware address on the network card. Now, this hardware address is very often referred to as the MAC address. And again, in the last video, when we talked about the OSI model, we talked about the sublayers and the media access control sublayer, okay, or the MAC sublayer. And again, we get down to MAC addresses. And MAC addresses are used with the data link layer, which is actually just below the network layer, or what would fall just below, in this case, the internet layer. So ARP is what we're going to use to take the IP addresses and then convert them down to the MAC address so it can be passed down the rest of the way through the OSI model. Next, we have ICMP, which stands for the Internet Control Message Protocol. This is responsible for diagnostic and error reporting. ICMP is what is used to attempt to make TCP/IP communications even more reliable. Basically, what happens is, if you were to send data and that data was unable to get to its destination, ICMP is the error message that would come back to let you know that it didn't get there. Now, the analogy I like to use is if you send a letter to somebody using the United States Postal Service and you send it to an unknown address, or maybe you send it to somebody who doesn't live at a certain address anymore, you get that letter back returned to sender. That return to sender transmission, where it comes back to you, is kind of like ICMP. It's not a guarantee of receipt, because that return to sender transmission may never get back to you, right? I mean, we've probably all sent a letter before, right? You have, I bet for sure, that just never got to its destination, but yet it never came back to us either, right? So there's no guarantee that anything is perfect, but those return to sender transmissions are an attempt to help make the transmissions more reliable. And the last one we have here is IGMP, which stands for the Internet Group Management Protocol. And I'll tell you what, the main thing I'll tell you that you should remember about IGMP is that it's not ICMP. I mean, if you take a look at just these four letters, ICMP, and you take a look at IGMP, well, first of all, the I, the M, and the P are the same. And the letters C and G, well, they look very close to one another. And when they're written out, sometimes, well, you might have the wrong one. So make sure not to mistake between the two. But basically, what is IGMP? Well, it works with multicast group memberships. Now, we're going to learn about multicast in just a few minutes here. But just know that IGMP is the protocol that works with the different group memberships within multicast communications. Okay, just kind of put that in the back of your head for when we get there. Now, speaking of multicast, well, before we get into that, we need to also talk about other types of TCP/IP communication, like unicast and broadcast, right? And then, of course, we can't leave out multicast. So let's take a look at these three types of TCP/IP communication. First, we have our unicast. With a unicast communication, it's what's known as one-to-one, meaning you have one sender sending specifically to one recipient. Okay, not that confusing, right? Unicast, one-to-one. One sender, one recipient. Now we can get into our multicast. Multicast is what's known as one-to-many. What we have here is one sender, and that one sender is going to then send to many recipients on our network, but not necessarily all of them. Okay, only the ones we have here in green. Now, where are these multicast communications typically used? Well, we were just talking about it a few minutes ago. Multicasts are typically used with things like streaming audio, streaming video. Only the people who are subscribing to the multicast transmission will receive that transmission. Okay, but this allows us to go ahead and send only once when we have something that is large in size, like streaming video. one sender sends it out, but then many different people are able to go ahead and receive that transmission. And IGMP is what is used to manage this group membership. Now, the last one we have here is broadcast. And with a broadcast, well, this is where we have one sender who's yelling out to everyone. Okay, a broadcast is, hey, everyone, got something for you here. Now, again, a broadcast is going to use UDP, not TCP, because obviously there'd be no way to go ahead and be able to make an acknowledgement of receipt from everybody. There'd be no way to establish communication with everybody in an efficient manner. You just kind of broadcast it out there, and everybody hopefully will hear it. All right, so those are the three types of TCP/IP communication. You have unicast, one-to-one. You have multicast, one-to-many. And then broadcast, which is one to all, one to everybody. Now, the next thing we need to take a look at here is the specifics behind these things called IP addresses. So, what is an IP address? Well, an IP address is a 32-bit address that is used to uniquely identify a computer on a network. Now, wait a minute. 32 bits? What does that mean? I mean, isn't an IP address, isn't it like 4 numbers with dots in between or something like that? Well, the reason we're saying it's a 32-bit address is because technically it's 32 binary bits. And that's why in just a little bit here, we're going to do some math. We're going to learn how to convert those 4 numbers with dots between them into binary numbers. Now, the IP address is broken down into 2 components. We have the network ID, and the network ID portion of the IP address is what identifies the network that a computer is on. Okay, so the network ID will show what network a computer is on. And there's another component called the host ID, and the host ID portion of the IP address uniquely identifies the computer on that network. Now, the analogy I like to use here is I like to think of this as being like a street address. Okay, we can break it down into the network ID is like the name of the street that you live on, and the host ID is the number on the building. Okay, so we break down to a unique location, a unique network, a unique street, and then we have to give it a number that's unique, specific to that network or specific to that street. Now, let's take a look at this. Here, I have an IP address, 192.168.10.1. Now, here's what we know. We know that the left side of the IP address is going to be the network ID. And we know that the right side of the IP address is going to be the host ID. Okay, that we know. That's there by definition. Left side is network, right side is host. The problem is we don't necessarily know exactly where the theoretical dividing line is. In other words, where does the network ID end and the host ID begin? Well, the way we determine what portion is network ID and what portion is host ID is with something called the subnet mask. Okay, and here I have added the subnet mask of 255.255.255.0. For right now, we are going to say that subnet masks can only be 255 and 0. That's the only numbers we can use in a subnet mask. And we're going to say that the 255s will always be to the left and the zeros will always be to the right. Now, we'll learn later on that this is not 100% true. But for right now, 255s to the left, zeros to the right, and those are the only 2 numbers that we can use. And the reason why is because the 255s represent the network ID portion of the IP address, and the zeros represent the host ID portion of the IP address. So in this example, what we have here is 192.168.10 makes up the network ID, or that is what network this particular computer would be on. And then just the .1 at the end represents the unique host ID on that network. Now, if we took that same subnet mask and we turned it down to 255.255.0.0, well, we change everything. Because now the network ID is 192.168. Okay, so that's what network we're on. And the host is 10.1. And guess what? We can even break it down further and say 255.0.0.0, meaning that we're on the 192 network, and our host ID on that network is 168.10.1. Okay, so the subnet mask is something that is very closely tied. Matter of fact, it's a required component to go along with the IP address. Without it, we have no way of knowing for sure exactly what portion is network ID and what portion is host ID. Now here I have a drawing of a simple network. And in this network, you'll see that we have our internet out here. And then we've got a firewall router. Now, I know these are terms we haven't really gone into yet, so don't really worry about it. And this router, we'll say, has an IP address and a subnet mask that's been configured. And technically, this router would have two IP addresses and subnet masks configured. There'd be one representing the outside connection out here to the internet. But the only one we're going to worry about for right now is the inside connection here. That's what this information represents. Because we're just looking at our own internal simple network here. And on this network, you'll see we have a server which has an IP address and subnet mask. And by looking at this IP address and subnet mask, we can draw a little line here, which represents that this computer, this server, is on the 192.168.10 network and has a unique host identifier of 201. And then on that same network up here, you'll notice we have a client with an IP address and subnet mask. And again, we can draw that little line representing that we're on that same 192.168.10 network, but we have a different unique identifier of 101. And technically, if we look at the inside of this router here, we have the same representation of the 192.168.10 network with a unique identifier of 200. So what that means is all of these devices, not including the internet, all of these devices are all on the same network. They all have the same network ID. So they all live on the same street. And they all have unique identifiers on that street. The client has 101, the server has 201, and the router has 200. Now, you may also notice that there's this thing here that says DG, right? There's another IP address that's configured. Well, that stands for default gateway. Don't worry about that just for the moment. I'm going to explain what default gateway is in a little bit. But this is how a basic network would be set up. Now, if we need to go ahead and get some of these IP addresses for our network, well, we need to know how to plan for an appropriate IP addressing scheme, right? We need to know how to get the right pool of IP addresses going for our network. So there's a couple questions you need to ask yourself when you're doing this. The first thing you need to ask is, well, how many IP addresses do I need today? How many computers do I have? Right? How many devices that require an IP address are on my network? The next thing I need to find out is, well, how many do I expect to need in the future? You always want to plan for growth. You don't want to just plan based upon where you are right now, because hopefully things grow, right? Now, the third question you need to ask yourself is, are you dealing with a pre-existing IP scheme? When you're looking at a network, are you starting from scratch? Is there presently just nothing there and you're building it from the ground up? Because these days, typically, well, everyone's kind of already got networks. So very often you have to kind of deal with what is already there. Sometimes you get to start from the beginning. Sometimes there's something already there and you say, you know what? I can't work with what's already here, so we're going to wipe the slate clean and start from the ground up. But that is a factor that you need to take into consideration. Now, what are some of the rules that we have with our IP addresses? First rule we have here is that each of the 4 numbers in an IP address is called an octet. And oct stands for 8, or 8 bits. Okay, and that's why, you might remember from a few minutes ago, an IP address we said is a 32-bit number. Well, that's because it's 4 8-bit numbers, and 4 times 8 is 32. So this 192.168.10.101 that we have right here, well, that's actually broken down in binary into 8 bits, 8 bits, 8 bits, and 8 bits, so as to make 32 bits. Now, each of these bits in binary would be either a 1 or a 0. And each octet can only have a number from 0 to 255. Now, why is that? Well, that is because if we have 8 zeros in our octet in binary, and we convert that to decimal, we're going to end up with 0. Now, I know we haven't gotten into the math lesson yet, but don't worry, when we get there, you'll see how this works. If we have all ones, which is the highest number that you can have in binary, the highest 8-digit number or 8-bit number you can have in binary, well, then you end up with the decimal equivalent of 255. And that's why every number you see in an IP address will always be from 0 to 255. Now, some additional rules for IP addressing. The first octet, or the first number in an IP address, cannot be 127. And that's because the 127 range of IP addresses has been reserved for diagnostics. Now, this is somewhat laughable, and the reason why is because of all the numbers that you can have that begin with 127, or more specifically, all the IP addresses that can start with the number 127, which, by the way, it's almost 17 million IP addresses. There's really only one primary IP address that is used for these diagnostics, and that's 127.0.0.1. And this is what's known as the loopback address. Sometimes it's also referred to as something called local host. Okay, so if you ever hear loopback address or local host address, that's 127.0.0.1. It just basically means myself. It represents me. Whatever computer I am, doesn't matter. You put in 127.0.0.1 means that computer. Now, some additional rules we need to keep in mind. I know, way too many rules, but you're going to need to know every one of these. The host ID cannot be all zeros or all 255s. And the reason why is because all zeros represents the network ID. Now, if we come down here, the example of that would be 192.168.10.0 is the network ID for the 192.168.10 network. And all 255s is what's known as the broadcast address. Remember the broadcast? We just talked about that a few minutes ago. Down here in the example, 192.168.10.255 would be the broadcast address for the 192.168.10.0 network. And what I mean by that is, if I need to make a broadcast, if I need to yell out to everybody, I got something for all of you. The way I get that done is by sending with the destination ID of 192.168.10.255. Okay, so in any given network, you can't have all zeros or all 255s for your host ID. Now, this is going to take us into something called class full IP addressing. Now, a little bit later, we're going to talk about classless, but right now we're going to talk about class full. Because originally, IP addresses were divided into different, what's called class ranges. Now, the A-class range of IP addresses all start with the numbers 1 through 126. What I mean by that is if you have an IP address and the first number in that IP address is 1 or 2 or 3 or all the way up to 126, then that, by definition, when using class full IP addressing, is an A-class IP address. And that A-class IP address will have the subnet mask of 255.0.0.0. Okay, so that means that 1 through 26, well, that's your network ID, just that first octet. Now, if you have an IP address that the first number is 128, 129, 130, etc., all the way up through 191, well, that's a Class B IP address. And with Class B IP addresses, the subnet mask is 255.255.0.0, meaning the first two octets make up the network IDs, and the last two make up the host ID. If you have an IP address that begins with the numbers 192 through 223, well, those are your Class C IP addresses, and they will have the 255.255.255.0 subnet mask, meaning the first three octets make up your network ID. Now, from there, we have our D class IP addresses, which begin with 224 through 239, and those are used for our multicast transmissions. And then we have 240 to 43, which are our E class, which are experimental. Now, the reality is you don't even need to worry about that. You can kind of draw a line here and say, who cares? We're not really worried about that. You mainly need to be familiar with A, B, and C classes when it comes to IP addresses that you can assign to individual hosts, individual computers. And then we have our Class D, which is really, you only need to know about it so that when you see one, you realize that it's a multicast transmission. Now, one other thing I want you to know about these A, B, and C class networks is that an A class network, because the first octet is the network ID, and you have 3 octets, each of which can be anywhere from 0 to 255. If you do the math, it means that there's almost 17 million hosts available. Now, the actual number is on your screen here. It's 16,777,214. Almost 17 million hosts. So there's only 126 networks, right? The ones that begin with 1, 2, 3, all the way up to 126. But you have a lot of hosts on each of those networks. Now, who do you think has the A-class networks out there? Right, your ISPs. Right, your internet service providers are going to be the ones that are going to need that many hosts. Now, from there, you have your B-class networks, which the first 2 octets make up the network ID. So you end up with the possibility of 16,384 networks. So quite a few more networks can be B-class networks. But because there's only 2 octets for the host ID, well, you end up with only 65,534 hosts on each of those networks. And I'll tell you what, most of those B-class networks are owned by your large universities, your colleges, things like that. Now, that's primarily because, well, they were part of the internet before most everyone else, and that's why they got those. Now, who does everyone else have? Well, your C-class networks, because the first 3 octets are for network ID, you have a little over 2 million networks, but each of those networks can only have 254 hosts. So, although there's a lot of those networks, well, you don't get a whole lot of computers on each one of those. So, these are your smaller to medium-sized companies that are going to have these Class C networks. Now, all in all, if you do the math, you end up with a total of just under 4 billion host addresses available out there. And it was originally thought that that would be enough. But as I'm sure you probably know, it wasn't. So there are some other things that we've done to help deal with this, but we'll get into that a little bit later. For right now, just taking a look at this, you need to know class full IP addressing. This was the original method that was used for internet communications with your A, B, and C class networks. Now, the first thing that I can mention to you, and well, I have to tell you, this is only a piece of it, but the first piece of how we were able to deal with the fact that we needed more than 4 billion IP addresses is through the use of private IP ranges. Now, there are certain private IP ranges which have been reserved away from public internet use. The first one that we have here is the 10 network, as it's commonly known, and it's an A-class network in which you have 10.000 all the way through 10.255.255.255. So the entire 10 network. If you see a computer that has an IP address that starts with 10, that computer cannot communicate on the internet. Now, before you get confused, you may think to yourself, wait a minute, I've seen that. I've seen a computer that starts with 10, and it is on the internet. Well, in a moment, I will explain how that happens, because it's the other half of how we're dealing with running out of IP addresses. We have a number of B-class ranges, which are also reserved, and that is 172.16 through 172.31. So 172.16, 172.17, 172.18, 172.19, all the way through to 172.31. All of those B-class ranges are not available on the internet. And then we have our C-class ranges, which are 192.168. Now, it looks like 192.168. anything, right? That's what it looks like here. But remember, these are C-class ranges. So actually, it's 192.168.0. That's an actual network, through the 192.168.255 network. Okay, so 192.168.0, 192.168.1, 192.168.2, etc., all the way up to 192.168.255, not available on the internet. So these IP ranges are used internally only. So if you have a network that does not need to be on the internet, you can use these IP addresses, and you can use them without having to worry about if somebody else is. It doesn't matter. You can use the 192.168.10 network, which is the same network that I'll tell you I'm using right here, right now. And that's okay. Why? Because your network and my network are never going to see each other. So there won't be any kind of a conflict. Now, before we go any further in explaining how this all works, I do need to mention that there's one other range here, which is 169.254.anything. This is a B-class range. Okay, 169.254.anything has been reserved, and this is used through something called a PIPA, Automatic Private IP Addressing. And this is something I will also explain to you a little bit later, but this is a way of computers automatically assigning themselves their own IP address. But again, those computers are not going to get on the internet. Now, as I mentioned, hosts assigned private IP addresses do actually have the ability to get to the internet, right? You've seen that before, but the way it's done is through a technology called NAT, Network Address Translation. Most of today's companies are actually using private IP addresses on their private networks and then using some form of NAT to get out to the internet. And when I say some form of NAT, well, I need to point out that NAT has a few different flavors. There's static NAT, there's dynamic NAT, there's actually something called PAT instead of NAT, which is Port Address Translation. But realistically, they all are of the same concept. This is definitely a scenario where we have one general technology and then a bunch of different people get their hands on it and then they have their own little flavors of it. So right now I just want you to focus on how NAT works generally rather than worrying about the different types of address translation. Alright, here's how it works. Here we have our own little private, and really I'll tell you what, let me kind of narrow this down. I'm going to do it this way. I don't want to include this other external IP address. So we have our own little private network here. Okay, and on this private network, you'll notice that we have a bunch of different clients. And I know it's kind of small, but I can tell you that they all have an IP address of 192.168.10. something. They have 101, 102, and 103 for their different host IDs. And then over here, we have a NAT server. Okay, that's what this box is right here. It's our NAT server. And the NAT server is, well, it's almost kind of like a form of a router. I know we haven't really gotten into routing yet, but it's going to have two network cards and it's going to have two different IP addresses. one network card is going to be connected to this internal network, and it's going to have an IP address which will communicate on that internal network. And that IP address in this case is 192.168.10.200. But then it's going to have another network card which is going to represent an external communication with the internet. And that external card will then have an external IP address which is valid on the internet. Okay, it would be one of our legitimate IP addresses that we use on the internet, not part of the private IP range. Okay, and here's what happens. Let me kind of clear this mess out of here so that you can see how this works. You have a client who makes a request to a website. That request will then be directed to the NAT server. The NAT server will then change the header information on that packet of information, that request. What it'll do is it'll change the source IP address from the client computer that we have up here, and it will change it to its own external IP address and then send it out on the internet. It'll then go across the internet and eventually get out to the web server that has that website that's being requested. Now, the web server is going to believe that this request came from the NAT server, not from the original client, because that original client has an IP address that's not valid on the internet. So this is the IP address. The external IP address of the NAT server is what the web server sees. So that is who the web server will respond to. Now, one thing that I didn't tell you that takes place when the client first sends this request to the NAT server. The NAT server will also cache that request. It'll put an entry into its cache saying, okay, client 1 was looking for this particular website. And the reason it does that is because when the response comes back to the NAT server, well, it retranslates the address based upon what client it knows was looking for that website. Okay, so when that response comes back, it looks in its cache and says, okay, who was looking for that? Client 1 was. So I'm going to retranslate. I'm going to, again, modify the header of that response packet and send that back on up to the client. This way, you see, the clients on our internal network are all shielded from, or I could say their IP addresses are all shielded from the internet, which means not only do we kind of help deal with the running out of IP address problem, and by the way, if you haven't figured out, the way we're dealing with the running out of IP address problem is, well, because I'm using 192.168.10 and you might be using 192.168.10 and somebody else might be using 192.168.10, and well, that's okay. We can all share that IP address because those IP addresses are never seen outside of our network. Only the one box that's communicating out to the internet needs to have a live IP address. So we only have to have 4 billion of those or less. So that is how NAT works. And again, there are many different flavors. As a matter of fact, if you're looking to get certified with CompTIA's Network Plus certification, if you look on the objectives, you'll see that there's SNAT, which is interesting because you have to look a little deeper into the glossary where they'll tell you that they're referring to static NAT, whereas I can also tell you that SNAT sometimes can refer to source NAT, or SNAT is also known as secure NAT. They mention PAT, port address translation. But I got news for you. They're all a form of NAT. They're just slight tweaks between the different forms of NAT. So make sure that you understand the general idea of what NAT is and how it works. It shields the private IP addresses from being seen out on the internet. And it also, likewise, provides internet connectivity to the internal resources. Now, before we go on, I will mention there's one other form of NAT, but not really. There's also something called a proxy server. And a proxy server is basically a NAT server, as we've seen drawn here. But the one added feature, well, really there's a couple of added features, but one main added feature is that the NAT server, or in this case would then be proxy server, will then not only cache who's requesting things, but it will actually cache the websites themselves, so that if another client makes the same request, that NAT server, or again, in this case, proxy server, rather than going out to the internet, it can just look in its cache and say, I have that, and just send it right back to the client. One of the other features of that proxy server, as long as I've brought it up, is that you can also do filtering, so you can say certain kind of content can't be looked at. But that's getting into a whole nother story, which we'll get into way down the road. Right now, I just want you to understand the basics of NAT and understand that there are many different flavors. So, I've been showing you these drawings of networks, and all these computers have IP addresses, but how do they get them? Well, there's three main ways that a computer can get an IP address. One way is statically, or what I could put as manually, because it means just that. It means you, the administrator, actually manually type in the IP address, manually configure it for that computer. Now, this is not very practical by today's networking standards, because if you have 1,000 computers on your network, well, it's going to take you a while to go around to each one of those 1,000 computers. Plus, you're opening up a whole lot of room for mistake. Right? You just accidentally make a typo on one, and now things are working all crazy on your network. Now, that's not to say that none of the computers on your network are ever statically assigned. Very often you'll have a dedicated server or something like that that might have a static IP address. But typically, most of our computers will actually get their IP addresses from a DHCP server. Now, what is a DHCP server? Well, DHCP stands for the Dynamic Host Configuration Protocol. And I'm not going to get into great detail about that right now, but basically what it means is you have a server that has a pool of IP addresses, right? Just has a list of IP addresses, and a client will dynamically go ahead and say, hey, I need one of those, and the server will look on its list, find one that's available, and say, here you go. Okay, so that is actually how most of today's computers get their IP addresses. Is you, the administrator, configure one server that has this pool or list of IP addresses, and then the server does all the work from there. Not only is that easier than walking around to 1,000 different computers, but there's a much lower chance of mistake being made. Now, there's a third way that I have listed here, and I mentioned this earlier, and this is something called a PIPA. That stands for Automatic Private IP Addressing. Now, with a PIPA, what happens is a computer will be configured to dynamically receive its IP address. And so it will think it's supposed to get its IP address from a DHCP server. It'll basically say, hey, I need an IP address. But when no DHCP server responds, well, then many of today's operating systems have a PIPA built in so that the computer can give itself an IP address. It'll say, I'm not getting any response, but I'm supposed to have an IP address. So I know what I'll do. I will randomly give myself an IP address that starts with 169.254. Right? That was that IP range that was reserved for a PIPA. And then what it does is it broadcasts out and says, hey, everybody out there, I'm 169.254.whatever. And if somebody else already took that one, right, maybe you have a bunch of computers all doing that, well, then you say, okay, I'll take another one. And then you randomly assign yourself another IP address. And you keep doing that until you get one that nobody has a problem with. And this works just fine on really small networks, because all the computers will all be on the same network. They'll all have the 169.254 IP address, and they'll all talk to each other. But there is no way to get to the internet with those IP addresses. There is no way to dynamically, through a PIPA, assign a router or a NAT server to do network address translation to get out to the internet. So a PIPA means that you really will be on a private network only. Okay, well, I promised you it was coming, and here it is, our math lesson. We need to learn how to work with binary numbers. So I have a question for you. I have a number on the screen here. It's right here. I'll underline it for you. What is this number? Go ahead, say it out loud. What is it? And it's not a trick question. It's just what it looks like. It's 3,482. But how do we know that? How do we know that this is 3,482? Well, that's because in the decimal numbering system, right, which is the numbering system that most of us typically use, we learned that each of the numbers fall into a column, and each of the columns have a value. And so here I've broken this out for you. We have the ones column, right? We have that here. We have the tens column, the hundreds column, and the thousands column. And then we take each of the numbers, 3, 4, 8, 2, and put that under each of the column values. And then what do? Well, you take the 3, multiply it by its column value. 3 times 1,000 is 3,000. 4 times 100 is 400. 8 times 10 is 80. 2 times 1 is 2. Then you add these numbers all together, and guess what you end up with? 3,482. Awesome! It works! Alright, now I know that probably sounds like a bunch of double talk, taking you in a big old circle, makes you want to say, alright, I'm done with your math lesson, Ed. Well, don't worry about it. I'm not trying to annoy you here. The reason I laid this all out for you in this way is because this is exactly how we are going to learn how to convert between decimal and binary numbers. See, decimal is what's known as base 10. Okay, it's the base 10 numbering system. And what we mean by base 10 is that each of the column values are known as the base, or 10. The first column to the right will be 10 to the 0. Then we have 10 to the first, 10 squared, 10 cubed, anyway, 10 to the fourth, fifth, sixth, etc., etc. And if we do the math using those exponential numbers, we get the ones column, the tens column, the hundreds column, the thousands column, the 10,000s column, etc., etc. But what we also mean when we say base 10 is we mean that the number selection, meaning the options that we have available to us in each of the numbers in the column, is 0 through 9, meaning we have 10 possible numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 possible combinations. All right, well, what does this mean for binary? Well, binary is what's known as base 2. Okay, and so if we have base 2, we are going to say that the first column to the right is going to be a value of 2 to the 0, and then 2 to the first, 2 squared, 2 cubed, 4, 5, 6, etc., etc. But what it also means is that the number selection in each column, well, we only get 2 choices, right? It's base 2, we get 2 choices, a 0 or a 1. Now here's the problem. The problem is that I told you that I was going to make this an easy math lesson. And you, if you're at all intimidated by math, probably got lost as soon as I said the word exponential numbers. I have had many students who have just completely shut down as soon as I said exponential numbers. The reality is that we don't need to worry about the exponential numbers or the exponential math. See, all we have to do is, well, the first number to the right. See, anything to the 0 power always equals 1. So the first number on the right is always going to be 1. And then from there, all we have to do is multiply by whatever base we're working in. So up here in the decimal system, we started with 1, and then we multiply by 10, and we get 10. 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000, etc., etc. Well, we can do that in binary. All you have to do is know how to multiply by 2. And that, hopefully, shouldn't be that difficult for you. So if we start off with a 1, right, we want to get rid of these exponential numbers over here. We start off with the 1. What's 1 times 2? 2. 2 times 2? 4. 4 times 2? 8. And if we keep going, we get 16, 32, 64, 128, 256, 512, 1,024, 2,048, 4,096. And we can keep going. I mean, I can tell you after that we have 8,192, 16,384. And, you know, I don't want to keep going and going. But we could. All we have to do is multiply by 2. And you may not be able to do this in your head, but if you can do it on paper, or if you can do it in a calculator, I don't care, as long as you have the ability to know these column values. Now, the reason we need to know these column values is because this is how we're going to figure out how to convert between binary and decimal numbers. Now, here I have an example of a binary number. Right here on the screen, I have 10101010. That's a binary number. It's all ones and zeros. But we need to convert that to decimal. So up here at the top of the screen, I have our column values, 1 through 128. Now, why did I stop at 128? Well, because this is only an 8-digit binary number, so we only need 8 columns. What we're going to do is we're going to take these 8 bits, these 8 binary digits, and we're going to put them under their column. And then we're going to multiply each number by its column value, right? 1 times 128 is 128. So we put that down here. 0 times 64 is 0, so I don't even need to include that in here. 1 times 32 is 32. Again, we have 0 times 16 is 0. Anyway, continuing on, we have 1 times 8, and we have 1 times 2, because basically all the 0 times anything is just 0. So the easy way to say that we do this is anywhere there's a 1, write that number, write that column value over here, and then we add that together, and we get 170. Now, this is why I started off with that 3,482 and showed you how we went full circle and how we got there. Is because this is how you figure out what a binary number is also. So the binary number of 10101010 is equal to the decimal number 170. And this is how we got there. Now, that's fairly straightforward, and people don't have too big a problem with that. But going from decimal to binary is a little more complicated. And this one does tend to throw people. So let me see if I can do this one with you and make it make some sense. Now, first of all, here's our column values all the way from 1 all the way to 4,096, just like we had before. That's why I stopped there. There was significance to stopping there. And here was the significance. What you want to do is take your decimal number and figure out the largest binary column value that can fit within that decimal number. Okay, so in this case, it's 2,048. See, 4,096 was actually one column too far, because 4,096 won't go into 3,482. But I wanted to put it there so that you could see why we're stopping at 2,048. Now, what you do, since that's the largest column value that can go into 3,482, is you put a 1 underneath there, and then you subtract 2,048 from 3,482 to end up with 1,434. Then you do the same thing all over again. What's the largest column value without going over? Well, 1,024. So we put a 1 under there, and we subtract it, and we end up with 410. Then we do it again. What's the largest column value without going over? 256. See, we're skipping 512. That's too big. So we go over to 256, put a 1 under it, subtract it, you get 154. Put a 1 under 128, subtract it, you get 26. Now we have to jump all the way down to 16, put a 1 under there, and subtract it. 8 goes into 10. 2 goes into 2, which leaves us with a remainder of 0. Now once we get to this remainder of 0, that's significant, because it means we're done with that part. And all we have to do is now take 0 and fill it into all the different column values that we didn't put a 1, right? Because that's our only choices, 1 or 0. So what this means is the decimal number of 3,482 is equal to the binary number of 1101100111010. Okay, where did I get this? Well, that's this right here. 1101100111010. that's a mouthful. So anyway, so that is the basics on how you convert from binary to decimal and then from decimal to binary without having to use a calculator, without having to know how to do exponential math, just knowing how to add, knowing how to subtract, and knowing how to, well, multiply by 2 so we can get our column values. You think you can do that? Well, I'll tell you what. If you can't, if you're not comfortable with that, you can use a calculator. And I will tell you that every single Microsoft operating system, and quite frankly, at this point, probably just about every operating system, Microsoft or not, includes a calculator. So what I'm going to do is show you how to do this on a calculator. If I go ahead and click on my Start menu, because I'm using Windows XP, you'll see here that I can go to the All Programs, Accessories, and you'll find a calculator. This opens up a cute little calculator that can do some basic addition and subtraction and a little multiplication, right? So this can help us adding our numbers and subtracting and multiplying by 2. But that's not what I'm talking about. What I'm talking about is if I go to the View menu here and change from a standard calculator to a scientific calculator, you will see that I have a lot more functionality here, including a couple buttons right here, one that's already selected, DEC for decimal, and one over here, BIN, which stands for binary. All I have to do is key in my number, 3,482, and click on the binary number. Bam! And just like that, we get our answer, 1101100111010, just like we had before. And if we want to go the other way around, well, I can go ahead and clear this out and put in 10101010, right? That's the one we converted just a little while ago. And do you remember the result we got? Well, if I click on decimal, that's right. It was 170. So you can do it quite easily with any scientific calculator, but I really want to present caution to you. And the reason why is because when you're working with a long string of ones and zeros, it is so easy to accidentally add or remove a 1 or a 0. And doing so will completely change the result. So let me give you a for instance. Let's go back to binary. Let me clear this out. I'm going to put in this binary number that we have down here, which is 1101100011010. Did you see what I did? Instead of 2 zeros right here, I went ahead and I put in 3 zeros. Now you might be looking at this saying, well, I wouldn't do that, but trust me, it happens. But if I take this new number with just an extra 0, I mean, that's all I added, right? Shouldn't really mean anything. Well, what happened to it? If I convert to decimal, we're nowhere near 3,482. Now we're at 6,938. So that's why it's so important to make sure that you do this very accurately if you're going to use the calculator. And this is also why I personally prefer not to use the calculator. Or actually, I'll tell you what I do. I do it on paper, and then I also do it on the calculator. And if I come up with the same answer, doing it both on paper and on the calculator, then I feel confident that I've come up with the right answer. So, how do we take all of this binary math and associate it with IP addresses? Well, you might remember that with an IP address, each of the 4 numbers in an IP address is called an octet, or an 8-bit binary number. Bits, again, are ones and zeros, and each octet can only have a number from 0 to 255. Why? Well, because all zeros, or 8 zeros, would equal 0, of course, right? And then 8 ones would, if you add up all the 8 first columns there, you end up with 255. Okay, and so that's the example I have here. All zeros, of course, is 0. That's easy. All ones filled into the first 8 columns here, you end up with 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, 255. All right, so that's why the range is from 0 to 255. All right, so we have an IP address, 192.168.10.101. What we need to do is take each of the numbers, starting with 192, and convert that into binary. So 192 if we convert it into binary, we end up with 11000000, right? And that's because 128 plus 64 equals 192. We take 168, convert that to binary, you end up with 10101000. 10 converts to 00001010, and 101 converts to 011000101. Now, one thing I want to point out to you is that because we are dealing with IP addresses, we always want to have the full 8 bits, even if they start with zeros, right? Before, when I showed you how to convert the number, we would have said that 10 just equaled 1010. But because it's an IP address, every single number has to be a full octet. So we represent it with all 8 bits and put the preceding zeros. So we end up with 192.168.10.101 ending up being the binary IP address of, I'm not going to read this to you, a 32-bit string of ones and zeros. Now we need to take a look at binary subnet masks. Remember we talked about having all 255s and zeros? And the 255s have to be to the left and zeros have to be to the right? Well, that's because technically the subnet mask is all ones to the left and all zeros to the right. 255 equals all ones and 0 equals all zeros. So we end up with a binary subnet mask in this case of 24 ones followed by 8 zeros. So if you put it together, you end up with 192.168.10.101 with a subnet mask of 255.255.255.0. That's how we know it to be in decimal. Well, that ends up becoming this long string of ones and zeros in binary. Now, don't worry if you're asking yourself, why the heck would I do that? We're going to talk about why we would do that in just a minute. Before we get to that, I want to talk to you a little bit about internetworking. Because one thing that I've told you before is that computers on the same network can talk to each other. Okay, fine. But guess what? Computers on different networks can't talk to each other without the use of a router. And a router, well, what is that? Well, I have on the screen this nice long definition. A router is a device that forwards data packets along networks. A router is connected to at least 2 networks, blah, 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 blah. This is the type of definition you would find if you look up a router on the internet. But what is a router really? Well, as I mentioned before, a router is something that connects networks together. So here I have some examples. Here's an example of a router being used, let's say, within an office. All right, we have 2 different networks. Okay, we have one network over here, and we have another network over here. So one's going to have one network ID, one's going to have a different network ID, and then the router is used to communicate between the 2 networks. Now, another example of where a router might be used is between the office network and the internet network. Or maybe even at home, right? You have your own little network at home and you want to get connected to the internet. So very often we will have a special type of router, which is called a cable modem or DSL router. And just to clarify, we're not talking about the cable modem itself. We're talking about a cable modem router or DSL router. Or another example might even be 2 offices that each have their own network that need to be connected to each other. And here I'm showing that there's actually 2 routers being used, one at the outside of each of the offices. And this would be an example of a WAN connection, where the router is actually getting you to the external media on each side. So a router, just to put it simply, is a device that connects networks together. Now, here is another example of where routers would be used in typical everyday networking environments. Here I have a main office which has many different networks which are all divided by multiple routers here. Matter of fact, this router in particular also connects with a WAN link to a router to a branch office. This router also connects us to the internet. Out in the branch office, we have another router which connects us out to the internet. Here we have another branch office with a router out to the internet. Hey, and here we might even have some users that work at home with a home network with a router connecting to the internet. These are all typical uses of routers. So I mentioned a little while ago the term default gateway, right? When we looked at our simple network, all of our devices had a default gateway configured, and I said we'll come back to that. Well, computers, as I mentioned a moment ago, can only communicate directly with one another if they're on the same network. Okay? Computers don't know how to communicate outside their network. The only way that that computer is going to be able to communicate outside of its network or with a computer on another network is through a router. And you'll notice that this is where we come back to the term internetworking, communicating between networks. Now, I know the word internet is in there, but it's not internet working. It's internetworking. And that's really where the term internet came from, because it's a lot of different networks all talking to each other. Now, the default gateway represents the IP address of a router that a computer will use to communicate outside its network. In other words, if a computer needs to send something to an IP address that's not part of its own network, where does it send it? It sends it to its default gateway. The default gateway will be an IP address on its network, and that IP address will represent the router. So here, going back to our simple network, you'll notice that the default gateway that both our client and server are configured with happens to be the IP address of the router, which it will use to communicate outside of its network, or in this case, the internet. So now we need to talk about a term called subnetting. Subnetting is the process of taking a large network and dividing it into smaller networks to increase efficiency and manageability. And I will tell you that there is both physical subnetting and logical subnetting. And very often, well, they go together. Here we have an example of a B-class network, right? We have our 172.16 network. And because it's a B-class, we have a little over 65,000 hosts. We also have a subnet mask of 255.255.0.0 so that we can truly know that this is definitely a B-class network. Well, what we can do if we want our network to be a little bit more organized than one big pool of 65,000 computers is we can break it into smaller subnets. And what we can do, and I'm actually going to jump down to the bottom here, is we can now have a subnet mask of 255.255.255.0. So we've taken the first 2 octets in our subnet mask up here, and we've made it that we now use 3 octets for our network ID. So we've sub-networked our IP address to include the 3rd octet, which means although originally our line was drawn here, now we're drawing our line here, which means we have divided this into 256 different networks, but each of those networks, or sub-networks as we could say, will each only have 254 hosts. We've basically taken a B-class network and we've sub-networked it into 256 C-class networks. Now, the reason we are talking about this, the reason we've been talking about all of this is because this all ends up playing into something called classless interdomain routing, or CIDR, or CIDR, or CEDR, or however you want to pronounce it. Now, what is this classless interdomain routing? Well, so we have some problems with our regular original classful IP addressing. See, with classful IP addressing, we have our class A networks, which have almost 17 million hosts. We have our Class B networks, which have a little over 65,000 hosts. And we have our Class C networks, which have 254 hosts. You see a problem there? There's huge gaps in between. So what would you do if you had 2,000 hosts, right? What if you were trying to put together a network with 2,000 computers? Well, we could either take a Class B network and have 65,000 IP addresses available to us, but we only need 2,000. And what that means is we're wasting over 63,000 IP addresses. Or we could take 8 separate Class C IP ranges, but then we'd have cluttered routing table entries, right? Because now we have these 8 different networks, and now we have to have 8 different entries. Actually, it's more than 8 entries. Entries on how to get to each and all of the 8 networks. Neither is a good solution. And also, I can tell you this is a huge part of the reason why we've run out of IP addresses. It's not just that we have more than 4 billion computers that need to get on the internet. It's that we have many companies out there that have way less than 65,000 computers, but yet they went and got a Class B network because they didn't want to have the messed up routing tables of all the different Class C networks. So there's all these unused IP addresses out there. So how do we solve this problem? Well, we do it with this thing called CIDR. And also another acronym here, VLSM, which stands for Variable Length Subnet Mask. Now what does that mean? Well, you remember before I said that your subnet mask could only be 255 or 0? Well, not anymore. Now we have the ability to go ahead and take our subnet mask, right, which was 255s and 0s. Right, we have that up here. And we convert that into a bunch of 1s and 0s. And the reason why is because, okay, we have our line drawn right here, right? We have 1s to the left, 0s to the right. Well, now what we can do is we can move that bar not just from dot to dot, but we can move it in between each one of the binary bits. So we can move it to the left if we need some more. We can move it to the right if we need a little bit less. And by the way, when I say a little more, a little less, the number of hosts that we need. Okay, we can put it pretty much anywhere we want in between these 32 bits so as to create options other than just 254, 65,534, or 16,777,214. Okay, so we have a lot of different options available to us. And now we have additional numbers that will be available to us in our subnet mask. It's not all 255s and 0s anymore. Now we do have to have all 1s to the left and all 0s to the right. That rule doesn't change. But our dividing line might be somewhere in the middle of one of these octets. And so if the line ends up coming down here in an octet, when we convert back to decimal, we'll end up with the number 254. Or if we move it over to here, we get 252. Or moving all the way down, we could have 248, 240, 224, 192, or 128. It's not just 255 and 0 anymore. So, how do we subnet using CIDR and VLSM? Well, let's go back to our example. If we start with 255.255.0.0, but we don't want to have a network of 65,000 computers, what we need to do is borrow bits from the host ID and move them into being part of the network ID. So what I have here is, you'll notice that originally this was our network ID, right? 255.255.0.0. So this was our host ID, right? We had 16 and 16. When we subnet, what we're doing is we're borrowing some of the bits that were originally in the host ID, and we're moving them over to being part of the network ID. Now, I've labeled it here that this is the subnet ID, but the reality is that there is a line that is now drawn here, and everything to the left of this line is now network ID. And now we have different sub-networks that we can create with these bits, and then our host ID can only be created with these bits. But notice that we did not have to move just between the dots. See, previously, the only other place we would have been able to move our bar if we wanted to subnet would have been right here. Okay, like we did before with our 172.16 network. Well, now we have the ability to go ahead and say, well, I didn't want to make 254 hosts per network. I wanted to have a little bit more. All right, so how do we figure out how far to move the bar? Well, you need to familiarize yourself with some formulas. And yes, I will tell you, now we're getting back into some exponential stuff. I only promised I'd make the binary math easy. When it comes to the subnetting, got to know a little bit about the formulas. Might even need a calculator. If you want to know how many subnets that you can have, right? So maybe you start with a pool of IP addresses, right? You start with your B class range, let's say. You got your 65,000 IP addresses. And you say, I need to divide that into X number of networks. Well, the way you figure out how many subnet networks are going to be available to you is by taking 2 to the n. N being the number of ones in the subnet ID. So if I go back, in this case, we had 5 ones. So what that means is, down here, I'm going to go to the example with these 5 ones right here. You get 2 to the 5, or 2 to the 5th, as it's more commonly said, would be 32 possible subnets. Now, what we also have to factor in is not just how many different networks we can create, but how many hosts we can have on each network. And that formula is almost the same. But in this case, it's 2 to the n minus 2. And the reason you have minus 2 is because, again, remember our rule that you can't have all zeros or all ones in the host ID. Oh, and I should clarify. N is the number of zeros in that host ID. Okay, so again, in our example, here we have how many zeros? Well, an octet would be 8, right? Plus 1, 2, 3. So we have 11 zeros in the host ID. So 2 to the 11, but in this case, minus 2. Okay, 2 to the 11 is 2048, but minus 2 makes it 2046 available hosts on each subnet. So in this example, this would be an example of a network that we want to divide into a maximum of 32 different networks, and each one of those networks will have no more than 2046 hosts. So if we go back to our example of wanting to have 2,000 hosts on a network, well then guess what? We want to go ahead and have a network with this particular version of the subnet mask. In other words, we want to go ahead and have a subnet mask of not 255. Let me clear this out. Not just 255.255.0.0, but 255.255. And we would need to convert this. And if we wanted to convert this, all we'd have to do is just make our columns, right? 128 plus 64 plus 32 plus 16 plus 8. And if you do that math, you actually end up with 248. So, let me take you to another example of a simple network. Here I have an example of a simple network, and I don't want to confuse you here because it's just a little bit different than what we were just talking about, because I just used the number 248. But here, you'll notice the 248 is in the 4th octet. Okay? So here I have a client with an IP address of 192.168.10.101, server with 192.168.10.201, and a router with 10.200. The subnet mask is now 255.255.255.248. Guess what? That is actually a simple bad network. It's not going to work. Why won't it work? Well, my client, my server, and my router all have these IP addresses with a subnet mask of 255.255.248. Looking at it in decimal, it's really hard to see whether it's going to work or not. We need to convert everything to binary. So what I have down here is I have the 3 IP addresses and the subnet mask broken down into binary. Everything in green here, you'll notice, is the original network ID, where we have all our ones from our original subnet mask, if it was a C class, if it was class full IP addressing. and everything was fine, right? Because everything matches on these three. But when we subnetted it, we went ahead and extended out this way, which means our line is now drawn here, which means that everything to the left of this line needs to be the same if they're going to be on the same network. And you will notice that although these two are the same, the top IP address, which was the client machine, we have a discrepancy right here and right here and right here, right? Where these guys are a 1, this is a 0. Where these guys are a 0, there's a 1. Where these guys are 1, this is a 0. And what that means is the client is on a different subnet, a different network. So how can we fix the network? Well, if we have a subnet mask of 222.55.248, then each network will be broken into blocks of 6 host addresses. Now, why is it 6 host addresses? Well, right over here, we only have 3 bits for our host ID, right? And 2 to the third minus 2 happens to be 6. But to lay this out a little bit more clearly, you can see that I have listed all 8 possible choices. Okay, all I've done is I've listed all 8 possible combinations of 1s and 0s, with these being the host ID. And with these, let me clear this up here, all being the same because they're all part of the same network ID. So that's 8 choices, but we have to cross the line through 2 of the choices, here and here. Why? Well, because 192.168.10.0 is the network ID, and 192.168.7 is the broadcast ID, which means the 6 in the middle are the ones we can actually use for our host IDs. Now, the one choice that we made here was to use the all zeros sub network, okay, everything in orange here. But we could have also made them all 00001. That would be a different subnet ID. And then again, we would end up with 8 possible host IDs, subtracting the 2 away, the one for the network ID and the one for the broadcast ID. So what we can do if we want to go back and actually fix our simple network, what I can do is go ahead and say that I want to use this subnet and pick 3 of the valid host IDs and assign them to the 3 hosts on this network. So here you'll notice I have 192.168.10.1.2 and .3. They're all valid, they're all together, they're on the same subnet. So if we go back to the simple network and fix it, you'll notice that now our router has .1, our server has .2, and our client has .3, and everything is working once again. So, I know this is confusing. I know it is. I've taught this for many years. But if you understand the basics, if you understand the basic concept of what an IP address is, you got your network ID and your host ID, you understand how to break that decimal IP address down into binary numbers and look at everything from binary, you will see exactly how the subnet mask correlates with the 1s and the 0s. The 1s represent the network ID, the 0s are the host ID. And in order for 2 computers to communicate, they have to be on the same subnet, or they have to all have the same network ID. So we need to figure out how to make this all come together, as we've done right here. And with practice, you will get this, but it will take practice. Now, the one last thing I want to mention to you before we depart from talking about CIDR is that CIDR technically is a notation. That's what it stands for. It's a notation. See, without the notation, we used to have to say 192.168.10.1 with a subnet mask of 255.255.255.248. Well, we can now simplify that by doing what's called a CIDR notation, which is where we just say our IP address and then put a slash and a number after it. And you know what that number is? It's the number of bits that represent the network ID in the subnet mask. So in other words, 255.248, well, we have 8, 16, 24 ones, right? We know that. And then 248 is 1, 1, 1, 1, 0, 0, 0, or 5 ones and 3 zeros. So you add 5 more to the 24, you end up with 29 ones. So the CIDR notation, if you ever see it anywhere, you see an IP address slash a number, well, that number tells you how many bits are in the network ID, and from that you can then convert to a proper decimal subnet mask if you choose to. Alright, so now that we know everything we need to know about IP addresses, well, I'm going to throw a little monkey wrench into the system. And that is that we need to talk about the new version of IP called IP version 6. Now we're just going to look at a high-level overview of IP version 6. We'll talk about why it was created, and we'll see what an IP version 6 address looks like and the types of addresses that are out there. But we're going to keep this pretty high level because IP version 6 is still somewhat something of the future rather than something of the present. Eventually, IP version 6 will be the primary protocol that is used, but for right now we're still using IP version 4, and IP version 6, well, you just hardly ever see it. But you should at least have a basic understanding of what it is and where it came from in order to be able to be successful when you run into it in the future. Now the first thing here is let's talk about what are some of the disadvantages or problems that we have with IP version 4. Well, the first one I already mentioned earlier. We don't have enough addresses. I mean, that's just the bottom line. There's a little less than 4 billion addresses, and as much as it seems like that should be plenty, it seems like that's a very large number, well, it's not. Relative to the number of people in the world, the number of computers in the world, the number of different IP-ready devices in the world, it's just not enough. Now, we've already started to solve this by using things like network address translation and private IP addressing and stuff like that, but we will eventually run out and we will have to have another solution. Now, another problem that we have is that today's internet routing tables are extremely cluttered. Now, this is because when the internet was originally created, we had to use what was called a flat routing infrastructure. What this means is that every single address prefix has to have its own route entered into the routing tables on the internet backbone routers. Now, as you can probably imagine, with the growth that the internet has recently experienced, and when I say recently, I'm saying over the last decade or so, we now have tens of thousands of routes entered into these internet backbone routers. And that's not good. That's a very cluttered way of doing things. Now, another problem that we have is that, although it may not seem like it, with IP version 4, it's very difficult to configure. Now, I mentioned a little while ago that if we want to put an IP address on a client, we have a couple different options, right? We either can do it statically, which is difficult to configure, right? It would take time and probably would have a lot of errors. And then we have the dynamic way of doing it. And we have a couple dynamic ways of doing it. We have a PIPA, which is completely dynamic and works and doesn't really require any administrative intervention at all. But the problem is that it's not routable. You're not going to be able to communicate with any other networks or the internet. So that doesn't really work. So the other dynamic choice is using a DHCP server. And I will tell you that using DHCP, it works quite well. The problem is that we still have to manage and maintain DHCP servers in order to allow all our clients to dynamically get those IP addresses. So still not the best solution out there. Now, the last problem we have with IP version 4 is that security is optional. Now, what I mean by security being optional is that there is something called Internet Protocol Security, or IPsec, that we can use to help secure transmissions. And with IP version 4, well, we didn't have to use IPsec. We optionally could use it if we wanted to try to be more secure. Well, in today's world, security is not really optional anymore, right? We really want to have mandatory security. So these are some of the problems that we face with IP version 4, and that is why they came up with IP version 6. IP version 6 provides solutions to each of these problems. Now, the first problem that we had is that we don't have enough IP addresses. Well, with IP version 6, there are plenty of addresses. There's no way that I can foresee us ever running out with IP version 6. And the reason why is because the number of IP addresses available is a number larger than I even know how to say. So the way it's most commonly presented is 3.4 times 10 to the 38th power. That's the number. Okay, so go ahead and feel free to pull out a calculator and try to see what that number is and then try to figure out how to pronounce that number. Good luck. It's a lot. It's a very big number. We are not going to run out. Now, the second problem we mentioned was the cluttered internet routing tables. Well, this too has been dramatically simplified and will be much more efficient because that flat routing infrastructure that I talked about a moment ago, well, now with IP version 6, it uses a hierarchical routing infrastructure. And this will make those backbone routers, well, the internet as a whole, much more scalable and will handle all the internet growth well into the future. Now, as far as configuration goes, I mentioned that that's not necessarily the biggest problem with IP version 4. DHCP does work pretty well, but you still have to manage the DHCP server. Well, with IP version 6, we have a very easy, very automated configuration solution. IP version 6 hosts will have the ability to automatically configure their own IP configuration without having to have a DHCP server. It works kind of like how a PIPA works, except for unlike a PIPA, we will have the ability to go ahead and get out to other networks. So it's all dynamic. You don't have to have a DHCP server, and we can still route to other networks. And the last thing, we talked about security and IPsec being optional before. Well, now it's mandatory. With IP version 6, IPsec is built in and used automatically. It is mandatory, so all transmission will be much more secure. Now let's take a look at what an IP version 6 address looks like. Now in IP version 6, our addresses are 128 bits long. Yes, that means there are 128 ones and zeros in this address. Woo! Look at all those ones and zeros. Could you imagine if I was to read that to you? You could probably take a nap before I was done reading them all. That's just way too much for anyone to look at. So what we're going to do is take the 128 bits and divide them into 16-bit chunks. Now, this is a lot like what we did in IP version 4, where we took our 32 bits and divided them into 8-bit chunks. But in this case, we're going to do 16-bit chunks. And then we're going to take each of these 16-bit chunks and convert them into a hexadecimal number to get an IP address that looks like this. Now again, this is not that much different than what we did with IP version 4. With IP version 4, we had 32 bits, we broke them into 8-bit chunks, and then we converted to decimal. Well, in this case, we're doing the same thing, but we're going to convert to hexadecimal. And what you end up with is 8 hexadecimal numbers separated by colons. Okay, so as you can see here, this is one hexadecimal number, and then here we have a colon, and then a second number, and a third, fourth, fifth, sixth, seventh, eighth. Okay, so that is what we end up with, as opposed to the 4 numbers that we had with IP version 4. Now, we can further simplify this by suppressing the leading zeros. So as for instance, here, with 05EE or 00FF or 0238, we can get rid of those zeros and we end up with this number down here where you'll see the 05EE just became 5EE, 00FF just became FF, and 0238 just became 238. But there is still one more step to simplifying the way this address looks. we can then express any single contiguous set of 0 blocks into a double colon. Okay, and so what we have here is, see, this is a 0 block, and a 0 block, which, by the way, I didn't point it out before, but you'll notice these were 4 zeros, and it goes down and becomes a single 0. Well, these consecutive contiguous 0 blocks now become just a double colon. Okay, and we can do that only once. Okay, if we had more than one contiguous block of zeros, we couldn't do it. We could only do it with one. And the reason why is because we know that there's supposed to be 8 blocks. So whereas now we have 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks, well, we know that this double colon must represent the 3 other blocks, and they must have all been zeros. So what we end up with is an IP address that looks like this. Now, if you're thinking that this is still more complicated than the average person can handle, right? And the average person can understand 192.168.10.1, right? But FE80:5EE:FF:238:47B1, no, the average person can't handle that. IP version 6 was not designed for the average person to understand. IP version 6 has been designed with such simplicity in its configuration that the only people that really need to understand these addresses are the network administrators who are going to take the time to fully educate themselves on this technology. So please understand that these IP addresses were never supposed to be easy for the average person to read like IP version 4. So now let's take a look at the different types of IP version 6 addresses. Now, you might be looking at the screen right now and thinking, well, this doesn't look that much different than what we went over before, and it's not. But there are some slight differences. I mean, the first thing we have here is we have the unicast, right, which is 1-to-1. Well, we had the unicast in IP version 4. But with IP version 6, there are 3 different types of unicast addresses. The first one is what's known as a global address. Now, one thing I should tell you about these unicast addresses, they are really similar to the unicast addresses we had in IP version 4. The global address was what was previously known as a public IP address, or just a regular IP address that was valid on the internet. So in IP version 6, the global addresses are the ones that are available to be used on the internet, the ones that will be recognized by the internet routers. The second type we have here is what's called a link local address. A link local address was just like the old automatic private IP addressing, or a PIPA address, where everything is self-configured on a host. But as I mentioned before, unlike the old PIPA addresses, which were very restrictive and you could only use on a really small private network, these addresses are more dynamic and can be used in much larger networks. Now, you can recognize a link local address by looking at the first block in the IP address. It will always start with FE80. If you see FE80 at the beginning of the address, then you know you're looking at a link local address. Now, the third type of unicast address that we have is what's called a unique local address. Now, the unique local address is very similar to the old private IP addressing. In IP version 4, we had certain blocks that were reserved for private use only and could not be used on the internet. Well, that's what we have here with our unique local address in IP version 6. There are 2 blocks that have been reserved and fall into these unique local address ranges. You will know you're looking at a unique local address if it begins with either FC or FD. Now, another type of IP version 6 address that we have is the multicast. You'll notice with multicast we have one-to-many. And guess what? This is exactly the same as it was in IP version 4. It's where you basically have one transmission and you have a list of subscribers who will then receive that transmission. That has not changed. But what has changed is you'll notice there's a new name here. Anycast. Anycast, check this out, one to one of many. Now, this is kind of confusing when you think of, well, let's see, one of, huh? Yeah, it's very confusing. So this is how it works. In an Anycast environment, we have a set of interfaces known as the Anycast group, which will listen on an Anycast address. Now, this is very similar to how multicast works, okay, where we have a group of devices which are all listening on the same address. When a host sends something to that address, the packet is then delivered to the one Anycast group member, which is closest or most accessible to that host. So what happens here is we actually have one-to-one communication just like a unicast, but the recipient is one of many recipients who all subscribe to this Anycast address, kind of like how a multicast works. So you could say that Anycast is kind of like taking unicast and multicast and bringing them together to create a new form of communication. So these are the three types of addresses that we can have on an IP version 6 network, and that's pretty much what you need to know about IP version 6 right now. You need to know the basics behind what it is, where it came from, what it looks like. Beyond that, as it becomes more and more heavily used, you'll become more and more familiar with it. All right, well, what do you think? Was that enough for one video here, all about TCP/IP? Well, after watching this video, you should now be able to describe the TCP/IP protocol suite. You should know that it's a 4-layer architecture based off the DARP model. There are many different protocols that work within each layer, all working collectively together to form this suite. You should be able to explain what an IP address is and decide on an address range which is appropriate for any given network. You should be able to figure out whether you need to use private IP addressing or if you're going to use public IPs. Heck, you could even use IP version 6, right? But you need to figure out what kind of IP range you're going to use to make your network work. You should know how to convert IP addresses from decimal to binary and from binary back to decimal. Matter of fact, you should be able to convert pretty much any number from binary to decimal or decimal to binary. You should be able to explain what a router is and how we connect networks together. You should be able to explain subnetting and decide when to use class full versus classless interdomain routing. Okay, remember, class full IP addressing, you got your A, B, and C classes, and you also have to make your dividing line, your network and host ID dividing lines on one of the dots in the decimal IP address, whereas classless interdomain routing, or CIDR, you have the ability to go ahead and put your dividing line in between any of the 32 bits in the binary IP address. And finally, you should also now be able to describe the basic fundamentals of IP version 6. All right, well, that's all I got for you. It was a bit of a doozy, so why don't you go ahead and give yourself a little break, maybe put a little caffeine in you, and I'll see you in the next video.